Hello students, in this video we'll prove Julia's lemma, which examines the behavior of the Schwarz-Pick theorem as you tend towards the boundary of the unit disk. So this is Julia's lemma. We'll call it Julia's theorem or Julia's lemma, doesn't matter, right? Okay, it's the same Julia from the fractal sets, right? Excellent. So it says, suppose that f is of course a shear function. That's always our setup for these problems. D into D closure like this is holomorphic. Okay, give you a holomorphic function, right? And a sequence Zn and these Zn's converge to the point 1 on the unit circle, right? Such that the sequence f of Zn also converges to 1. And then one technical condition, one rate of growth condition on the difference quotient, and 1 minus modulus fn of z over 1 minus mod Zn. Looks like a difference quotient, right? Converges to a constant c as n goes to infinity. Okay? Under those three conditions, then what do we have? Then we have the result of Julia, which says that modulus 1 minus f of z, f of what? Yeah, f of z squared over 1 minus modulus f of z squared is less than or equal to this constant c. And then 1 minus z modulus squared over 1 minus the modulus of z squared, okay? So it takes a linear inequality and turns into this quadratic one. Now it's important to know where the moduli are, right? This is 1 minus f of z modulus squared, and the denominator is 1 minus the modulus of f of z squared. Similar over here, the same structure. I have 1 minus z modulus squared and then 1 minus the modulus of z squared, right? So it's important to understand where these moduli are coming in, okay? So how do we prove this? So the proof goes as follows. So by Schwarz-Pick, what can I say? We have this. We have f of z minus f of zn over 1 minus f of zn bar f of z is less than or equal to z minus zn over 1 minus zn bar z, like that. Okay, that's Schwarz-Pick, right? The zn are fixed points in the disk, right? And then I can, for any z, I have this inequality over here. Beautiful, that's what Schwarz-Pick tells us, okay? Now, here's a little technical lemma, right? So lemma, that's easy to prove. We proved it in our Blaschke video. It says what? It says that, like I said, about 1 minus the modulus of a Blaschke product. If I give you a Blaschke product, w minus z over 1 minus w bar z squared, what that turns into is it turns into a 1 minus modulus z squared, 1 minus modulus w squared over modulus of 1 minus w bar z squared, right? And the proof of this lemma is just a calculation. So the proof is a calculation in our Blaschke video. Proof is a calculation from our Blaschke video. Okay, it's easy to verify, okay? Nonetheless, that's an important lemma and what we're going to do next over here, because what I'm going to do is I'm going to use this lemma, and then I'm going to take Schwarz-Pick and square it. That doesn't change the inequality, right? Good. And then I'm going to do 1 minus this is bigger than 1 minus this, right? So now by Schwarz-Pick, I know that 1 minus modulus of z minus zn over z, 1 minus mod zn z squared is less than or equal to 1 minus this expression over here squared, f of z minus f of zn over 1 minus f of zn bar, f of z like this, squared, right? And now I can use our lemma. What does our lemma tell us? Our lemma tells us that this is exactly equal to what? this is going to tell us that, let's see over here, I'm going to have a 1 minus mod zn squared, 1 minus mod z squared, over 1 minus zn bar z squared, like that, is less than or equal to, same thing over here, 1 minus mod f of z squared, 1 minus mod f of zn squared, all divided by what? All divided by mod 1 minus f zn bar f z mod squared. Now we're done, essentially, right? Because what we're going to do is I'm going to rewrite this over here. This implies what? So I almost see what we want over here, right? So I need to see an f of z. I need this over here. So this is going to stay put, okay? And then what else are we going to have? We're going to basically put this in the denominator. That's going to go on the other side, right? And this is going to go on the other side, right? And also this is going to go on the other side, okay? And what's going to go over here? Well, what am I going to take over here? I'm going to take these guys over here. Those guys definitely are going to go over here, right? And then the modulus of z, where is that going to go? So then both these terms over here, oh, it's going to happen. Perfect, yeah. Good. And so these two terms now, this term is going to stay where? So let's make sure we have all the terms we want. And then the modulus of z, this is definitely going to go over there as well. And then this term over here, I think we're good to keep it. Now we want to put it over there as well, right? Good. So we're just going to flip what? We're just going to flip these two things. So that tells me what? The pink terms over here are what? Are 1 minus, that's going to be the denominator. So the numerator is going to be what? The numerator is going to be what? The numerator is going to be 1 minus f zn bar f of z over 1 minus modulus of f of z squared. That's on the left-hand side. And then less than or equal to what? Now what's on the right-hand side? So those two things go in the denominator. 1 minus mod z squared, 1 minus mod zn squared. Okay, those are in the denominator. This goes in the numerator. This 1 minus zn bar z squared. And then what's left over here is just going to be this expression over here, this modulus, this expression, right, which is going to be a factor of 1 minus mod f zn squared, like that. Good. Now let's think what's happening over here. So notice over here that this is really what? That this is really going to be, it's a difference of squares. It's going to be 1 minus mod f, so this is going to be 1 minus mod f zn, and then 1 plus mod f zn, right? 1 plus mod f zn. Let's give us some more space over here. So that's what this numerator is. Let's rewrite that. So this term over here is exactly what? This term over here is going to be 1 plus mod f zn, and then 1 minus mod f zn, right? That's what this term is over here, by difference of squares. And this term over here is what? Is 1 minus mod zn times what? Times 1 plus mod zn, like that. Now, f of z n and f and zn both converge to 1. So this goes to 1, and this goes to 1 as n goes to infinity. That goes to 2 over 2, nothing. 1 minus f of zn over 1 minus zn, by assumption, goes to c as n goes to infinity. So as we let n go to infinity, what happens over here? As n goes to infinity, this becomes what? This becomes the numerator. Well, f, that's going to 1, right? And that, of course, is squared, right? There should be a squared over here. Yeah, that's a squared. So I'll have a 1 minus f of z squared over 1 minus mod f of z squared is less than or equal to, again, this is 1 over 1, that's 2. That goes to c, so it's going to go to c. And then this goes to a 1 minus z modulus squared over 1 minus what? 1 minus modulus of z squared. Perfect, and that's exactly our that's exactly our Julia theorem result. Beautiful, right? Now, of course, what you can do, it's easy to see this actually. So all I can do is now, you don't need to assume that they go to 1, right? So in other words, you could assume that this one goes to what? That this goes to alpha, and this goes to beta on the unit circle, right? On the torus, And then what you can do is you could apply Julia to the function g of z, which is going to be what? Which is going to be a b bar and then f of a bar z, right? And if you do that, what does the result turn into? The result, therefore, turns into what? It turns into a, it goes beta minus f of z squared over 1 minus f of z squared less than or equal to that constant c, and then I'll have alpha minus z squared in the numerator, and then the denominator I'll have a 1 minus mod z squared. So in other words, if you replace this one over here with a beta and that one with an alpha, then the result of the Julia theorem or the Julia lemma is still true if instead of converging to 1 on the boundary, you converge to a point alpha on the boundary and a point beta on the boundary. Now this Julia, the boundary behavior becomes extremely important when you start to study functions, when you start to sort of merge the theory of complex variables with real analysis, and you want to figure out when the boundary limits of these analytic functions exist, right? Because oftentimes we might be in a position where the maximum principle will not necessarily apply, because if I have a function defined from the unit disk to the unit disk, the radius of convergence might be 1. The boundary behavior of that function on the unit disk might be absolutely atrocious, right? It might be very wild. It might be highly oscillatory. So I can't necessarily take an analytic function from the disk to the disk and extend it continuously to the boundary, right? So if you want to analyze carefully the boundary behavior of these holomorphic functions, you need to use results like the Julia lemma and non-tangential approach, slots, domains, and different types of things, which are really important in the study of the Hardy spaces, which we'll eventually get to when we talk about more advanced topics and complex variables. Thank you very much.